a second. Great. Yeah, give me a sec. Super tired. Went to bed late. Usually I get up at 6, but I got up at like 8. All right. Given with that, like I don't have stream set up, so just give me a moment. I'm gonna go write the agenda. What's the date today? 2026. 7. Seven. Not the 17. It's the 7. And what's the next one? The 9th. Okay. Question is, what are we doing? What are we doing this stream? What happened last stream? Yeah. Oh yeah, optimization. It fixed the reassociation. I just like fixed a bunch of stuff. I think what I can I mean, let me just think for a second. Because I wrote this out. I wrote this thing. This is like the plan. This is the plan. I don't know if I'll go I don't know if I'll explain it. It's basically everything that give me a moment. It's like everything here, but everything here, but it's not it doesn't have like, this is like more detailed. It's more detailed. Implement more optimizations, probably proof automation for the conv stuff. Oh, that's important. This could probably just be a simp though. 3D printers? Maybe. That would be nice. Almost more optimizations. Maybe because a lot has changed between now and then. This proof needs to be salvaged in some way. Okay, so proof automation. Okay. All right. Last time to now. If basic ACC lemmas. Okay, so it's just a lot of cleanup, like the entire thing. Last time to now. Entirely cleanup. most basic optimizations, and the OPT rewrite lemma tactic is now O rewrite lemma. To be in line with rewrite. Okay. So proof automation for this. Okay, so this is gonna be copied. Here, implement more optimizations. Salvage the proof for reassoc. This entire thing is under salvage the proof of reassoc, and then implement some more instructions. Yeah, more instructions. More optimizations. Probably take from the Go compiler. Rules file. Probably take from there. Okay. Salvage the proof for reassault, because if you look at okay, yeah, so most of the stuff has been changed. So did I show everything got moved out, right? Yeah, okay, this got moved out of experiments. Okay, so this was moved out of experiments. So that's good. That's yeah, so that you guys know about that. Okay, so yeah, opt rewrite. Okay, so there's two things I need to show off. The new file structure and the ORW tactic. So let's go to the reassoc. Let me just salvage this proof. Let me just salvage it real quick. Okay, adcom. Where's that from? Oh, it's from theorems. Basic. Oh, come on. Okay, what is it missing? Where's adcom? It's here. Tactic rewrite did not find an occurrence of the pattern in the expression. Where's adcom? Shit, that's a problem. Why is that not working? Simp? Let's just add. Should we write it like this? Just give me a sec. Add. Oh. Okay. We'll just fix that soon. We'll fix that soon. Okay, so I'm gonna upload this. I'm gonna upload this. And then we can go find it. This is the one. Okay, we'll get started. All right. Welcome. Hello, everyone. Thanks for coming back. It's been a while. It's been. What week is this? I mean, this is stream 7. 1, 2, 3, 4, 5, 6, 6, 7. 7. Seventh stream. This is the 7th stream. So what is this? That's like we're like in week 4. We're in week 4 of this. So that's not bad. It's been a while. So we've been slowly getting work done. So between last stream and now, it's really just been a lot of cleanup. So it's just a lot of cleanup. So really, with the file structure, if you look at the file structure, right now, most of the things are the same. Like we moved we moved up to here, right? We moved up to here, and that's like staying in place. But what we also did was what I also did is in the inst. It used to be called, I think it used to be called llvm. What I did was I basically like extracted all of the instruction definitions and I just moved them to a different file. So now they're in a different file and they have like some lemmas here. So they're all in a different file. In the reach set of files. So it's just like easier to maintain. And in here I like write this as well as the notation for them. This notation should be this. Okay. And then what else changed? OPT, yeah, so OPT rewrite. And then so in there's like a folder called core in theorems now. What I've done is basically underneath core there's something called basic. In basic, it's just like all of the like basic theorems that you just like need to have. So like for example, for no sign wrap, right? If you're summing 2 bit vectors and you know they don't overflow, that's just equal to that's just equal to adding the 2 bit vectors. This is kind of like constant propagation, right? For example, if you have like I don't know, like 255, like 250, 254 and 1 is an IN8, right? What you can do is like if you add them like this, like what you can do is you just literally add them, right? This is like a constant propagation. This is like a const prop lemma. So the reason for this kind of syntax, this kind of like weird brackety syntax, this is for if you write bracket a, it's like equivalent to just writing bitvec. It's kind of just like a nice way of me like writing bit vectors. It has some like further like use. The point of these like little like tack thingies is just like signify that this matches a constant value. This matches a constant value. So if you were to use this as a rewrite rule, if you looked at the theorem statement here in the rewrite rule, you would just see like these squares and squares rewrites to a square. So these squares are basically constants to match. They just let you know that these are constants. So it won't match on like it's just different. It's different to just writing x. It's like very different from just writing x. So that's the reason. So these are just a bunch of basic lemmas. So like for example, like if you add two numbers and you know they overflow, that's just poison. So it's literally just like all of these for the instructions. So it's just like basic. Yeah, so here's like the basic lemmas and then refinement. So for example, like if you sum with no sign wrap, this is just like rewriting to x plus y, like up to poison. Same for all of these. This is just refinement. So you're stripping the flags and you're just like refining the instruction. And there's also just like no wrap refines to no unsigned wrap, no wrap refines to no sign wrap, for example. And then like AC lemmas. AC stands for associativity commutativity. So there's add com. That's like super basic. Add, no sign, wrap, com. They're all com. They're the amount of UB that they produce. The UB on the left hand side is like exactly equal to the UB on the right hand side. So you use equal sign. You don't use this. Well, obviously this is true, but you would want to use you would want to use equality. You would want to use equality. Yeah, so add a sock. So yeah, add no sign wrap a sock left. So you strip. It's basically stripping all the flags and then moving the brackets left. Same thing for right. The add no sign wrap a sock like all positive and all negative. These things, right? I don't think these have been updated to work with the latest lemmas. So these aren't in here yet. This is a bit of a more complicated theorem that doesn't live in this binary, like doesn't live in basic. But for basic, right, just the refinements, right? So if you strip the flags and then you can change the brackets. Strip the flags and change the brackets. Same thing for sub. So subtractions, more of the same thing. Refinement, the exact same. Multiplication is a little bit different, mostly the same. Actually, it's closest to the additive ones. This thing's the same, sort the same. AC lemmas, it's associative. What else? Not much. Okay, divisions where it gets different. This is just makes sense. SDiv 0 equals poison, of course. Int min SDiv -1 is equal to poison. So the explanation of this is, let's say you got int min, negative int min. What is negative int min? This is an negative int min is an overflow. The explanation for that is, let's say you have the int data type. This goes from 2 to the, so this goes from -2 to the 31 to 2 to the 31 minus 1. So this is int min is this thing, right? If you were to negate this, you would basically you remove the minus signs, right? You'd be going to this, right? But this is outside the range of int. It's outside the range, so that's an overflow. That's just like straight up an overflow. So if you were to do int min divided by -1, what's that? That's just like this. So that's poison. Yeah, that's poison. So that's a thing. So yeah, that's like another condition to watch out for. I think it's also the same for multiplication. So if I think like if you just multiply by -1, multiplying by -1 also I think also does that. I think that's also, I think I should add a lemma for that. But yep. The reason why this is a lemma is because division actually has a check for this in here. So I gotta add it. So yeah. So const udiv, const rewrite. Yeah, this is just udiv. So there's signed division and unsigned division. So as per 2's complement, so add sub mul in 2's complement, addition, subtraction, multiplication, they're basically they're basically the same for unsigned and unsigned. Unsigned and signed. They're the exact same. But division is different for signed and unsigned. So there's sdiv and there's udiv. And these are the two like different ones. So that's why I need to have sdiv and udiv. So udiv and sdiv is mostly the same. Refinement lemmas. Did I only got up to... Oh, okay. Refinement lemmas. Like the only refinement lemmas exist. Is just this one, because you can't refine like an sdiv into a udiv. Like they're different. They're different. So you can only strip tags, flags, and the only flags I have is udiv exact. Udiv exacts here. So yeah, the division has to be exact. If it's not exact, it's poison. So you can refine this and strip the flags. Like that. So yeah, that's everything in basic. That's everything in basic. So and then for bitwise, it's literally just like for all instructions at the top they have poison propagation. So it's just like a simple lemmas that's like poison on the right, the whole thing's poison. Poison on the left, poison on the left, the whole thing's poison. Same thing for bitwise, in comparisons. So I've only really fleshed out this one. So that's the lemmas. That's all the lemmas. So what else changed is OPT rewrite. I don't think I've explained this tactic. Basically, what it does is if you have a goal with a form like this, right? Let's say you had as a hypothesis, LHS rewrites to LHS that, right? I had that as a hypothesis. What you could do is you can do OPT rewrite H, and then it will just transform the goal into this. It'll basically like find LHS and just like replace it. That's it. That's what OPT rewrite does. It's just like a super nice tactic that is a lot small. It's like it's a lot lighter than using the like proof automation like program like infrastructure things. It's just a much lighter. It's just like one folder, one file. So I changed it. I changed it to be this is called O rewrite now. It's called O rewrite. So if you do O rewrite, it's the same thing, and you can just like spam the lemma as well. So it basically like works exactly like rewrite RW. Works exactly like RW. Do I have examples of its use? Oh, they're here. Yeah, I have examples of its use here. So I mean, I can just show you. So O rewrite, start here. O rewrite will just rewrite. That's it. Super simple. And then there you go. So O rewrite literally just see this is the goal state. This is a lemma that takes no sign wrap rewrites to x plus y. Obviously you want to get rid of the flags here, right? So you remove them and add a sock. That's it. So yeah. It's like a nice little tactic. It's just like O rewrite RW. It's following from the tactic like the naming conventions of like mathlib. So mathlib has like grw. This is like generalized rewrite. If I had mathlib, I believe I could just like never write this. I could just like not write this tactic and like just put like use a generalized rewrite. But I don't want to depend on mathlib. I don't want to depend on mathlib. Because that would be really silly. I don't want to depend on mathlib. So yeah, I had to like implement it myself. So I did this like a long time ago, and then between now and last stream, I changed the name and like modernized it a bit to use like the rewrite stuff. Okay. So let's see. So we want to salvage the proof for reassoc because I didn't change anything. We want to salvage the proof and then we'll implement some more instructions. That's it. So let's salvage the proof. So like what's even wrong? So I don't know why. I don't know why adcom is giving me this, right? Because if you look here, there's so this is a IN. This is an IN type. That's an IN type. You're calling add on them. It's IN add. IN add is literally the exact same as like this. It's just the exact same as that. So I don't know. I don't know what's going on. I think it's because the way I define that. We'll just let's see. It's like here, right? Type classes, like, I bet this is the problem. Okay, so I define the type class like this. Why? How do I make a type class like... Maybe it's like reducible? I want to be able to see through the type class. Because, for example, right, adcom, right, if you look at it, adcom uses the plus here. This plus is this type class, and it should forward it to this, and it does. The thing is that rewrite can't see through it. This is the same. This is in add. That's in add. But rewrite can't see through it. So I think putting reducible there will like make it. I hate type classes. And when I change something, like, I hate that like lean's slow. Yeah. I mean, it's not. It's slow. It's fucking slow. I need to switch to the module. There's like a module system. Lean has a module system. I can switch to that. Blood. What? That's annoying. I know it's like have by, it's just like, see, I can rewrite this with like adcom, and then like, I don't know, how do I like desimp this? See, okay, this doesn't run. It's the exact same. I don't know why. I seriously don't know why. I seriously don't know why. Have adcom. Why? What's the problem? Oh. Okay. And then like, I don't know, desimp at this. How do I see through these? Maybe what I do is I can just change the definition. Yeah. I'll just change the definition. It's probably better. It's fine. Rewrite adcom. I mean, that's probably gonna work, right? It's probably gonna work. Surely it works. Oh, you're kidding me. Oh, wait. Unfold. Okay, that works. That was easy. So that was easy. I wonder, maybe I can... Okay, so the proof is like basically salvaged at this point. But maybe I can make... I want to deal with the unfold stuff. Oh, yes, OPT reassoc. Verify IR expert. Unsupported expression. What's the problem? Oh. Okay, I need to fix OPT as well. I need to fix refication. Give me a sec. I need to fix that. Yeah, give me a minute. Okay. Fixing this, the reason why it's unable to denote this expression, the point is that here, these things, the squares mean nothing. This is just like a pretty printer. Under the hood, it's bitvec4. Under the hood, it's that. So that's not an issue. This is an issue. So these adds here. So previously, the way I defined this is like this. I define it like this. This caused issues because when I use plus on something, it'll always try and use this, but plus is used for like 10 different things. So I define it using a type class, which is what you're supposed to do. It's what you're supposed to do. The issue with that is it can't see directly through to this. It always has to go through the type class. So for example, if I were to write x plus y, it'll basically like desugar down to h add. It'll like let's do like check. It'll desugar down to h add. Yeah, it'll desugar down to h add and to this, and oh no, it takes in like 3 different things. It takes in the type. How does this even work? What? Okay, H has a type class that takes it. I actually don't know what this desugars down into. But I know it. Okay, I know it's like hadd xy instance of whatever the instance is defined for. I think we can do this, right? Run elab. Turn 1 something, right? We'll check this out. So let a equals quote plus 2. Oh. QQ. Yep, and then log info. Why? What's the problem? Really? Oh. Okay, well that's 1 plus 2. Is it a 2x? What? Oh. This is just an expert. Oh, I don't have any... Okay, I gotta write lean at the front. Oh, okay, so it's this. So it's hadd. It's hadd. Yeah, hadd with... So it's nat inst hadd. Inst hadd nat. Let's check. Inst hadd nat. Yeah, this is the annoying thing with using hadd. Because it uses like a bunch of type class shit. It doesn't go straight to the thing that you wanted. How did I solve this before? Let's see. Okay. How I solved this before is not dealing with hchat at all. So I'll show you. I think the files are deleted. Yeah, the files are deleted. Let me open like an older version, because that was a trick. There's a trick that I use that I can just remove all the instances. It's the like hchat instance. Maybe it's in shared. Damn, that's annoying. Is there a way for me to just like switch to this? Dude. Am I already on this? No, I'm not. God, there was a trick that someone showed me in the Lean Discord. Okay, basically what the trick did is it ran a function. So all I need to do is on refi. Yeah, on refi. Before I call refi IR expert, right? On the expert. Before I do that, I basically do it's like transform expert, and it's just like this is just like a function. This is like a function that removes all of the instances. It's like simp, but for instances only. I'll see if I can find it because I need to like. What's this from? Let me just find it real quick. Um, what the fuck? Why is the search so shit now? Instance. No, like transforms a thing. So annoying. Fuck, this was ages ago. Give me a sec. Oh, here it is. Nice. Okay, this thing, basically it runs transform and removes classes. It removes classes. So I just do that. So yeah. I don't even need to run this recursively. I can just do it on the thing. So unfold projection instruction. How did this thing use it? So if this is none, just return like some. I don't want to return. Is there like... This is an option. Okay. And this is like get D. Get D body? Get D body? Why? What's wrong with this? Can't lift over a binder. Blood. Why can't I do that? Oh. Okay. This Lin is the worst error messages. As the worst. You just need to be in the know to actually, like, I don't know. The error messages, they just suck. Okay, so this should fix everything. It should fix everything. But it might make the denoting bad. But who knows? We can just fix that. So, reassoc? Yeah, we'll just give this a give this a go, and we'll see what it does. Unsupported expression, add. Dude. Can't you just... I have to keep rerunning it in a loop. This is like a recursive thing. It'll just like keep going. I need to keep going. I need to keep unfolding until I can't stop unfolding. Okay. Maybe I can use imperative. There's literally like repeat. You can just like you just run a piece of code forever. Let not body. And all I need to do is I just need to keep doing this. I just need to keep doing this until I don't have any more. So if some, then break. What's the problem? Oh, if you let. Okay. Break. No, you just keep going, and then you break, and then this is the one that you want. I need to like hide this. So this is body tack, and this is real body. Great. That should work, right? That should work. Yeah. Why? Unidentified body. Oh. Fuck, that's annoying. Okay. I need to implement this as... Yeah, sorry. Give me a moment. I need to implement this better. Actually, it wouldn't matter. No, it shouldn't. The issue is that was body Q. Okay, give me a second. Body to body. Okay, the issue is I renamed this body to be something else. I like this is a function. What you can have is you can have a where clause here. And in this where clause, you can put other functions. These functions are kind of like little like closure kind of things, because anything in here, you can access in here without even passing it in, which is nice. But I'm trying to access the body, and the body's in here. But the thing is, I changed the body here. But I don't think this makes much of an issue. The only reason I changed the body is to perform matching. That's the only reason. So I think it's fine. I think that's just like fine. But who knows? Who knows? Okay, why? Why? What the actual fuck? Is it reification or denoting? It's reifying. I hate that I have to wait. Why is it not unfolding that? Hold on. Let's see if I can make this reducible. Let's see if this changes anything. So it's reducible now. Great. Instead of trying to fight against it, I think I'll just match normally. I'll just do this. So how does it look? It's INN. So it's like this. So it's add the type, the instance, and the two expressions. Okay, that should be better, I mean. Yeah, that should be better. And what's the... Okay. That should work. I mean, I hope it works. Oh my god, what a pain in the ass. Why? Oh, it worked. Okay, the issue is that it just didn't transfer back into the thing that I wanted. So in denoting, I need to use the actual add instance. Let's see. This one's the one. So what I pass is, this is LHS, RHS, the constructor name, the inst name, instruction name. Instead I pass, I should change this into expr. Okay, so instead of passing a name, I need to pass an instance expression. So I'm just going to put expr. Just put expr here. And yeah, unfortunately, these have to all turn into mkapp. It's annoying. Can I just do name or... Name or expr? Why... Why can't it just like automatically cast? Alright, we'll just take a look at how BV decide does it. I mean, wouldn't hurt to like just check. Wouldn't hurt to check. No, I don't. Yeah, they do H and. I guess I like... It's probably fine. I'm just gonna change this to match on H end anyway. Yeah. When they call reify, it's binary reflection. Because they never have to go back. They never have to denote back. That's the thing. How does add work? Add takes in the type itself, and then it takes in the instance, and then two of the types. Okay, I pass in a name. I pass in a name. Inst name is heterogeneous. Is it heterogeneous? Homogeneous is heterogeneous instance. So basically how it works is the instruction quoted, it's just going to work like this. So I guess if is a homogeneous instance, then do something else, do that. What is it? What do we write? So what people are going to pass in, people are going to pass in this. People are going to pass in add.add. Oh, that's a problem. They're going to pass in add.add. As well as the add instance. What's this called? In inst add. So call this inst add. Okay, so how it will work is h is a sum option name. So people can pass two things. So they'll either pass in this, right? These two names. Fuck, that's annoying. Yeah, they'll pass in these two things. So if this is true, so if let some hinst. So basically, it's basically this mk app, okay, const mk app const the inst name, and we want to pass in the type. We want to pass in the type, which is this INQ. That's the type. Yeah, so it's HAD. How's HAD work? God, so annoying. No, I don't want to restart. Oh, fuck off. Oh, so fucking annoying. Well, of course there's a problem. Zuber. Oh, hey. Oh, sorry. Have I not? Sorry, I haven't been looking. I haven't been looking. I'm used to the chat being empty. Sorry. Sorry. It's good. It's good to see you. It's good to see you. Sorry about that. Supported expression. Oh, come on. Thought I fixed that. Oh, it's H and. What? Okay. Okay, well, I mean that worked. Okay, so I just want to. All I wanted to do was take a look at this. I hate metaprogramming. Okay, that's worse. Okay, that's a lot worse. I can't, I can't read that. Okay, here. So it's hey Chad, type, instance, two things. Okay. Hey Chad, type. Okay. So when I write this, what I'm supposed to write is, hey Chad, hey Chad, and the instance for that. Oh, that's annoying. Okay, I rather let because this takes an inst hey Chad, which then is like another indirection of things. I'd rather just write add some inst add. Okay, I guess that works. Okay, so hginst. So if we have hginst, I mean it's just that. So it's just like mkapp3 or something. Is that fine? I hope this works. Oh, what did I put? I put this in the wrong place. Good one. Oh, I need to put universe parameters. I don't want to do that. I'll do this instead. Really? What's the problem? Unknown identifier. Oh, because I need to use do notation. Damn it. It's annoying. Okay. Inst n needs needs some more stuff. It needs this with the bit width. What's wrong with this? What? Syntax is so inconsistent. What is going on? Why is this unknown? Holy crap. Undo? Oh. What? Thanks, Lane. It doesn't take any explicit arguments? Maybe I just put nothing. Maybe that does something. I don't know. To check what body is, I'm just gonna try this. Maybe I can get a printout and see what I actually need to put in for add. There you go. Okay, so it's in add. It's this thing. With the type, the instance, and the two expressions. I mean, that should work. This is... okay. Is there a way to only fill in universe parameters? I was provided explicitly using the option type. M none A. Oh, that's great. Okay. Wow. Okay. Well, that's basically exactly what I need. MK app. For this thing, does this need universe parameters? This is the question. Does this need universe parameters? Shouldn't. Okay. So then I can just do this. MK app. Inst n with n. MK apt MK app. Why does this need universe parameters? Okay. That's valid, right? Oh wow, it works. Okay. What? In the argument this has type of this of sort type. Would expect it to have type. Type. Or yeah. Okay. I don't get it. Has type add. Iron add inst add. Maybe I just let type. Maybe I just let inference do it. No, I can't. Alright, so this is being passed in explicitly. This is being passed in explicitly. None. Ah, this is annoying me. Well, something happened. Oh, it actually worked. Huh. It actually worked. I need to put HAD though. Because otherwise it's not going to display right. Yeah, I'll put HAD. Oh, it worked. Okay. God, that was annoying. Whatever. That's okay. There we go, it's fixed. Wow. Yeah, it actually does the thing. Okay. What a waste of time. But that wasn't that bad. So the proof's fixed. The proof's salvaged. What I need to do is I need to fix these unfolds. Maybe I can make this nicer. Nicer, like by adding simps. Maybe I can make this a simp. Maybe I'll make this a simp. Let's see what it does to this. Oh. Okay, made no progress. What if I write it like this? I mean, is that the same? Simp made no progress. It should simplify this. Oh, I'm stupid. It's not even... Yeah, sorry. This is the completely wrong theorem statement, and I'm like hallucinating or something. Eval add. So eval add needs to be a theorem that basically takes this to this. Unfold this on the right. That was easy. Okay. And then eval... I guess, running simp on this should do things. Okay. It's doing something. It removed all the consts. Okay. Okay, that should work. And then theorem eval const should be const. So, what does const look like? It's just this, right? It's just that. It's a natural number. Fair enough. This does let me get rid of simp for a sec. I want to see what this const stuff does. So const con. This is being casted into this. Yeah. So this is bitvec of type this. This is oh, I mean, I guess it's the same. I guess it doesn't matter. It's just this, right? So what's the theorem statement really? Okay, that's a cast. So I think I should just like bitback of nat. Okay, oh, even decent works. All right, eval const. That's also a simp lemma. Okay, that's annoying. That's like really annoying. Okay, I prefer the like the cast. Oh, come on. It should be simp only. Okay, better. It's better. I can just like skip all of this. Rewrite to that. And then bitvac add equal add bitvac. This is not a real thing, right? Oh, it is a real thing. Oh, I need to remove this. So what if I just like simp? Is this some extra like? You should run these. This needs to be turned into like a simp lemma as well. So bitvac a plus b is just equal to synthesize implicit argument. Okay. Okay. Oh, come on. It's annoying. Why is it bitvac of nat? It's annoying that it goes to that. Is that better? Does that work? I think it's add a sock as well. Really? Does that prove it? What's left? That's not helpful. Oh, because I need to rewrite com at some point as well. Is it here? Or is it here? Somewhere. God, I hate that these are being rewritten to that. Because it's so hard to read. Note, Mathlib would like this to go in the other direction. Yeah. Me too. What are you talking about? Sim made no progress. How do I cast? Okay. Yeah, that's good. That's what I wanted. Okay, so I need to rewrite with associativity. No, I need to. Hmm. I need to call this twice. Okay, so it's conv RHS. The other way. Okay, or the other way. Yeah, and then this is the one I need. That's not helping, but this is helping. Oh, come on. LHS. LHS? Ah, there you go. God, that was painful. That was painful. So what I'm going to add is to this guy. Right? And then we'll do the rest. Basically just modernizing this proof. Okay. Oh, this is going as well. Oh, wow, that's the proof. Okay. And then simp. And then rewrite twice. And wow, that's much better. This thing is a simp. That's this case, this case, this case. Great. All right, that wasn't that bad. So I think I'll call this solved for the moment. This is solved. This is gone, right? Do I even need this? This is gone. I don't need this. The solution to this is doing it properly. Oh shit. I guess it might be better to not do this properly. This is truncate, get truncate, truncate. I think I'll use the lemma, like staying in this. I'll use that. I'll just keep that. Okay. So we can commit this. This is not that bad. Tactics. Whoops. God, I hate fucking Copilot. I can't disable it. Why can't I disable it there? Okay. Sure. Fixing. Oh. Note for. No, for opt. It didn't need. Hold on. Let me just check Wi-Fi real quick. Denote. Okay, that's better. So what needs to be changed is not this. Okay. Fixing Wi-Fi and denote for opt. Okay. Maybe. Um, we got time. I'm gonna go to the bathroom, get some water, and then maybe we can do some proofs. We'll do some proofs. Hello. Okay. I'm back. Just give me a sec. All right. Okay, let's do some real stuff. So if we go to the Go compiler, the Go compiler is really nice. So Golang has like implemented everything, has implemented the entire compiler stack, like everything, all in one. They have their own SSA, they have all their optimizations, they have everything, right? Which is nice. So we can steal from them. So what they have these things called rules files dot rules. This is like generic rules is for general optimizations, and then they have like these kinds of rules. For example, WebAssembly, right? They change the. This is like this is what you run in the middle end. This is like the middle end optimizations. Like, obviously, like this is const prop, right? If you floor something, it's just like flooring the value. Oh, most of these are const props. Like multiplication by power of 2, that's just a shift. Things like these. And then they turn these like generic like these like middle end instructions and they do lowering. So this is like instruction selection. Um yeah, so in here there's like wasm add, right? Surely. Yeah, like equal 0. Like these are WebAssembly instructions. So yeah, they like do lowering. So we're not really interested in like uh platform dependent, like architecture dependent. Where's like AMD? Yeah, like these, like LEA, LEAQ, things like that. We're not really interested in those things. Um, I wonder what WebAssembly has. Copy sign. Yeah, these are WebAssembly, 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 WebAssembly. Yeah, WebAssembly. Okay, so this is we're basically just gonna steal from this. So let's just do a bunch of that. Just gonna do that. So it would be nice. So all this constant folding stuff, like I can just do at home. It'd be nice to turn multiplication into a shift. Convert multiplication by power of 2 to a shift. Okay, we'll just do that. Um, this is like canonicalization. Yeah, canon. Um, why is these erroring? Like what? What the fuck? Like I hate this. So annoying. God, leave me alone. Fuck. Okay, there's identity. Identities is moved in here as well. Okay. What does identities import? Nothing. Let's import this. So the theorem statement. I think I have power of 2 definition. Okay. Theorem statement. Let's actually write this. So theorem mul how power of 2 rewrite yeah. Okay. So polymorphic on bit width. So if we have this is an X, right? x multiplied by constant c multiplied by a constant c. We also know that c is a power of 2. We change it to this, right? Bitvec n. Yeah, this is a power of 2. This is a prop, so it's an inductive proposition. Well, I'm not defining it like that now. Like this, right? Okay, and it's just like c is power of 2, is power c 2 nat is power of 2. Is power of 2. Yeah, so obviously like this implies that c is non-zero. Because 0 is not power of 2. Yeah, so our hypothesis is c power 2 constant. So this is basically saying this rewrites to what's like log 2 of that. So this rewrites to x shifted this by c log 2. I mean, I guess that's right. Maybe I'll change this. Right. Create log 2 for bitback. Okay. So the proof of this, I wonder if this is, because this creates no undefined behavior. This creates no undefined behavior. I believe there was an equality. Well, let's just verify this for like small n. Theorem. Yeah, let's verify this for like small n. So let's do like 8 or something. 8, 8. Well, I don't think we can verify this. Oh, okay, yeah. This is not an equality because of poison. Unroll. Because X can be poison. Oh, but I guess it doesn't matter. No, it doesn't. Okay. So it is an equality. Is there fin? Is there fin.log2? Oh, great. To fin. Okay. Um... So we know that this is equivalent to multiplying by 2 to the vat, and 2 to the log 2 of something is just that thing itself. So I guess instead of, like, you can't really verify this. guess I'll change this to net. That's fine. 2. Okay. So let's make an auxiliary lemma. This is basically saying if I have x shifted by a value, this is equivalent to me multiplying by 2 to the value. Two power. Oh, that's the width. So expected F type nat. What the fuck? What if I make this nat? Thin n. That's better, right? Okay. The costs everywhere make this so annoying. P bind fine if n equals 0. Oh yeah. This is what you're always supposed to do first. I don't know why I didn't do it. Okay. Simp only. That's not very useful to me. I wonder what grind does with that. Nothing. Let's cut that. Okay, whatever. Is there a way for me to just unwrap the value? Because I can just like turn this. These are just like, this is like const prop stuff. I need to create these for bitwise. So let me just do that. Theorem. Hold on. What is LLVM's? What is LLVM semantics for shifting? that's valid. That structure shows a point of poison value. If it shifts out any non-zero bits. Yeah. Oh, this is valid. This is fine. The thing about this is these semantics might be too strong. This might be like overextending. I'm gonna like listen to that, but I mean, it's fine, probably. So this must be a rewrite, because this creates poison. I guess I didn't know that. Given the condition that... Yeah, so this rewrites to this. Like this, right? This is not... Surely it's not by RFL. It's just not. No. Okay, so it's poison... if this is... If the bit width is 0... You have to prove that this rewrites to 0. What? What does this do? What is a gnat? This should be easily, like, dispatchable. Because this is basically saying, if the bit width 0, if A and B have bit width 0, this should just go to 0. Let me pin that. Let me write a theorem for this real quick. Okay, well, it didn't pin it at all. You're fucking kidding me. Okay, so if these are 2 bit widths, like n, n equals 0 implies that... I mean, given this, right? Surely it would use this. I mean, why? Surely, like... It's not... Is it going to use this? No, it didn't. This is very brittle. B.2 nat. This only works on nats? Maybe I need to... I wish I could restrict the amount of lemmas. You know, it'll be easier. It'll be easier if I do it like this. This is a bit with n. Right? That's an n. These are all n's. Okay, so it's just by cases equals 0. This is true. Subs h simp. Maybe we can write this theorem. So if I have this, this is equal to 0. Whoops. Injectivity, exact. Is it like inject, injective? Okay. So is that a thing? Is it gonna use this? Yeah, I mean that should clear it. And then these are just this is non-zero. So then simping this, it should use h. Oh, that was easy. What the hell? Okay. All right. So this needs to go in bit. Const shift left. Now that's not very useful for us. because this has a rewrite relation. We don't want that. So we want this, given the hypothesis that B through nat is less than or equal to is less than n. Um, so this is just true. I believe I could copy the proof as well. Right, I could. All right. In the basic lemmas, it'll just say, yeah, so theorem. Shell poison. So I'll just do shift left const. So A can be anything. I think I can just copy the proof in the same way. Oh. Oh shit, okay. So I also need the thing that the bit width is non-zero. The bit width being zero is so could be zero is so annoying. Do I use this anywhere? Oh, I use it here. Yeah, I need to pass that the bit width's greater. Ah, so annoying. Okay, what else? Well, we have n is less than b. What's the problem? It's annoying. Remaining subgoals n equals 0. But that's a contradiction? That's not a contradiction. Okay, that's not really helpful. So I can't really prove this. That's annoying. Why are my definitions defined this way? So annoying. I really hate LLVM's model of undefined behavior. Like, I hate it so much. I hate poison. I hate this. I hate. Why do I have to model poison in this way? This this isn't how like machines, like, this isn't how CPUs work. This is annoying because I'd really like to make these like junk definitions, but I can't. I know, like, the fact that this is like polymorphic for all n, this makes this entire thing like a junk definition. Hmm. Maybe for shifting. Maybe for shifting, I get rid of this kind of b is greater than n behavior. Um, I mean, I don't know. the proof of this, like, proof of this is like annoying. I want to lift these up into two nets. How do I, two net LT? Maybe that's useful? No, it's not, because this brings us back to the start. These kinds of things are like really hard to encode. Because B depends on N. I don't know. I might change this condition. I might change this condition. What does WebAssembly do? That's a good question. Where's the shift? Well, I know that. I know that. But the semantics of this copies like x86 in some way. This is the text. I want execution. God. Ah, it's so slow. Why? Why is it like this? Oh, it's dark reader. Whoops. Show. Where's show? V shift up. Why vector instructions? Bin up. actually can't search for any of this. Okay, thank God. Yeah, so K is that modulo N. That's what x86 does. So this is shifting modulo N. Now, is that better? I genuinely don't know. Hold on. What's 0 modulo 5 0? It just leaves the thing as it is, which is actually what I want. Yeah. Probably. Probably. Then I don't need to do these. That's equal to that. That's equal to that. 0 is not an issue anymore. Oh, I mean, I guess it is an issue. Oh. Come on. I think some more thought needs to be done at home. Like, I need to think some more about how I'm actually encoding these instructions. Because following LLVM like maximally, like just literally copying their instructions, it makes things like really annoying. Like proving things like symbolically is really annoying. And then simp.in is like a bit of a sledgehammer here. It does too much. It does way too much. And if it can't simplify, it leaves with you like an unmaintainable mess. I don't know if I'll do this. Maybe I'll make an instruction that does this. I'm going to make an instruction that does this. It's just the issue is like, I don't know. The problems are that when I'm encoding like a hypothesis like that, I'm using like b dot like 2nat. I really don't want to do that. Which is annoying. Maybe I encode, maybe instead of this, right? Maybe instead of this, I do le with b. As like an actual hypothesis. And then not that like fake one where it's like b2 nat less than n. Because then that can become a decidable proposition as well. I think I'll leave that till next time. I think I'll leave that till next time. I'll write the agenda. So I'm gonna commit what we have. Okay, it's not bad. And then this thing. What's so bad about this? I don't know why this is not compiling. Yeah. Oh, these need to be undone. I'll just put that there as like a reference. Oh. Okay. How's it usually go? How do I write this? Okay. There are a H that yeah, improving side. I guess the problem is yeah. Getting in a better way. Like POW2 for IN. LT width. For into POW2. Yeah. IN LT width B. Focus on not exposing lean. Instead of N is like if I have like where's it like N is greater than or equal to 2. Width greater than 2 or lean specific. Yeah. Okay, I mean that's not that bad. I mean this is good to have. This is fine. This is yeah. I can just do this. So I'll just put that up. How long did we stream today? What was it like? Hour and a half? 2 hours and a half? Yeah, 2 hours and a half. Well, it's not 2 hours and a half. It's like 40 divided by 60. So it's like, yeah, 0.6. 66. Okay. Yeah, I'll check this again. All right. Goodbye, everyone. We did get some good stuff done. We got these done. Proof salvaging. I think today was just a lot of busy work. Yeah, there's a decent amount of stuff that I need to think about. The good thing I have these streams. When I have these streams, I'm put on the spot, and I need to like improvise and just think a lot. So usually, like when I'm alone, I'm not really thinking about these things. I guess that was useful. All right, bye bye.